Okay, it is the 5th of September 2025, approximately 2:06 p.m. Let's get into exercise 28 in Dummett and Foot. So, exercise 28 starts off with, oh, that's not good. This thing is just about out. Let me check this. Okay, good to go. So, exercise 28. That's much better. In exercise 28, we're told let a under multiplication and b under composition. Well, we'll just call this closed circle, open circle operations. Be groups and let A cross B be their direct product. We want to verify all the group axioms for A cross B. So, more specifically, we'll break this down into 3 parts. So for the first part, we want to prove that the associative law holds. And let me see this. Okay, yeah, because there's a table corner here and I don't want to write too far. Okay, so prove that 1, 1 is the identity of A cross B, and C, prove that the inverse of A comma B is A inverse comma B inverse. This is kind of this will be interesting for group actions later. So, yeah, the intuition of this. Well, let's think about this intuitively. The rule on A cross B is component wise, right? So, A sub 1, B sub 1, cross under the closed circle operation A cross B, with A sub 2, B sub 2, A sub 2 comma B sub 2 is equal to A sub 1 closed circle A sub 2 comma B open circle B sub 2. Since A and B already know how to associate, well, they don't know things, they're, not conscious beings, but since, by the structure, they're able to associate with their identities, where their identities exist and how to invert, doing everything in parallel, and each coordinate should inherit all axioms immediately. But let's look at this a bit more rigorously after I check that everything looks fine. Yeah, okay. So, ooh, is this better? Is this better for that? I don't know. Yeah, that works better. So I'm not allowed to move this board. I am allowed to move the eraser, so that's good. But I think my eraser's better. So let's do this with the proof. The binary operation on A cross B is defined by A comma B, open parentheses A comma B, open parentheses A sub 1, B sub 1, comma B sub 1, close parentheses, times, open parentheses A sub 2, comma B sub 2, close parentheses, equal to, open parentheses, A sub 1, close circle operation with A sub 2, comma B sub 1, open circle operation with B sub 2. Since A and B already know, it's like, no. Okay. So the binary operation on A cross B is defined by this. So open parentheses A sub 1 comma B sub 1 close parentheses operating with times open parentheses A sub 2 comma B sub 2 close parentheses is equal to open parentheses A sub 1 close circle operation with A sub 2 comma B sub 1 open circle operation with B sub 2 close parentheses. We can say, well, let's just start with this. Later on, we're going to say that 1 denotes the identity in the relevant group. So I want to say context should be used here to determine whether or not it's in A or B, but we'll see whenever we get there about like actually just why not putting it as one sub A or B, right? So for closure, if open parentheses A sub 1 comma B sub 1 close parentheses comma open parentheses A sub 2 comma B sub 2, if these are within A cross B, then A sub 1 close circle A sub 2 within A and B sub 1 open circle with B sub 2 within B. And so, well, what can we make out of this? So remember earlier we looked at well, suffice to say, let's just say this. Okay, so open parentheses A sub 1 comma B sub 1 close parentheses open parentheses A sub 2 comma B sub 2 close parentheses is equal to open parentheses A sub 1 close circle operation with A sub 2 comma B sub 1 open circle A sub 2 close parentheses within A cross B. So that's the case if we're saying that if we start off with these coordinates, I guess you could say these coordinates, right? If we start off with these coordinates already existing within A cross B, then each of these exists within, by operation, with elements within A belonging to A and with B belonging to B, then we can extend that to say, okay, so we have these coordinates and we operate them with each other, then we get this. We get this by the nature of the group itself. So that exists within A cross B. That is within A cross B. Not does exist. We know it's in there. So, and where it is, I don't know about that, but roughly speaking, there. Suffice to say, we know it's an element of A cross B. So closure works. It's closed. So let's move on to associativity. Right. So for associativity, we have, well, you know, how we would usually prove this is just by grouping them leftward or rightward, right? So with three different parts. And for this case, it's no different because, well, we have four open parentheses, A sub 1, comma, B sub 1, close parentheses. That's an element within A cross B, where I is equal to I is equal to 1, 2, 3. So that allows us to do this writing as open parentheses A sub 1, comma, B sub 1, close parentheses, open parentheses, A sub 2, comma, B sub 2, close parentheses, open parentheses, A sub 3, comma, B sub 3, close parentheses, which is equal to, you know, so this is an operation, right? So we perform the operation, we expand that. So what we get is open parentheses, A sub 1, B sub 1, close parentheses, open parentheses, A sub 2, dot, close circle, A 3, comma, B sub 2, open circle, B sub 3, close parentheses. Now, and we'll continue along this line here in a moment. Take my swig of coffee and check the camera. So we have here, So open parentheses, A sub 1, close circle, open parentheses, A sub 2, close circle, A sub 3, close parentheses, comma, B sub 1, open circle, open parentheses, B sub 2, open circle, B sub 3, close parentheses, close parentheses. So we just continue expanding this, even though, you know, it's a bit tedious, but it's, I mean, is it in comparison to what, you know? But let's, so open parentheses, A sub 1, close circle, A sub 2, comma, B sub 1, open circle, B sub 2, close parentheses, open parentheses, A sub 3, comma, B sub 3, close parentheses is equal to open parentheses a sub 1, comma, b sub 1, close parentheses, open parentheses, a sub 2, comma, b sub 2, close parentheses, open parentheses, a sub 3, comma, b sub 3, close parentheses, and using associativity in, let me just fix this. Okay, let me check to see that, I haven't missed anything though. Because, it's one thing to have it in your notes, and it's another thing to actually make sure that what you wrote in your notes is actually accurate, so. Yeah. Yeah, okay. So, let's go back to the original statement, which is, we want to verify all of the group axioms, and here we have clear direct succession of steps that show that yes, indeed, it is associative. Look at where we put the parentheses after all. They're different now. They're grouped rightward instead of leftward. We've proved that these things are equal. Ergo, associativity holds. Now, let's go on to the identity. So, for the identity, let open parentheses 1 comma 1 close parentheses denote a pair of identities from A and B, right? Okay. I know I said I wanted to do the whole A-B thing, the 1 sub A, 1 sub B thing, but I think it's pretty clear from context which one belongs which because of the order that we established A, B existing, right? So what I mean by that is like from A and B, and then we say that, okay, for any A comma B within A cross B. So it's like, well, it should be pretty clear that, A goes here, B goes here, A goes here, B goes here, right? So let's just take a step back, and I'll relent to say we'll use context in this case. So unless if it becomes like really important that these things, like really important that these things are actually equal to each other, and we weren't supposed to presume that that would be the case based on where they're placed. Okay, so for any AB within A cross B, open parentheses A comma B, close parentheses, open parentheses 1 comma 1, close parentheses is equal to open parentheses A, close circle 1 comma B, open circle 1, close parentheses is equal to open parentheses A, comma B, close parentheses. That's for one of them. Now let's go to the other. So 1 comma 1, open parentheses 1 comma 1, open parentheses A comma B, close parentheses is equal to, well, what exactly? Well, it's equal to open parentheses 1 close circle, yeah, because we're operating with A, so anytime we're operating with A, in case you couldn't tell, we're going to be using the closed circle operation, and anytime we're operating with B, we use the open circle operation. So, open parentheses 1, closed circle A, comma 1, open circle B, and what is this equal? Well, it's equal to open parentheses A, comma, b, which is what we wanted. We wanted that. So thus, open parentheses 1, comma 1 is a two-sided identity. In A cross B. Ooh, okay. Now, what do we have left? We have the, like, okay, we gotta prove that every element has an inverse. So let's get to that. So, inverses, right? So, for open parentheses A comma B close parentheses within A cross B, let's let open parentheses inverse of A comma inverse of B be the component-wise inverse. But it's not enough to, just sort of say this thing is this thing exists, behold, right? So you gotta prove that, okay, it works under what we want an inverse to do, and that's contained, that equals the identity, right? And we already proved that the identity exists. So if we can prove that, okay, multiplying, well, not multiplying, well, I guess operating, the actual pair with the inverted pair, that will indeed give us our identity. That's what we have to prove. We can't just say, let the let the inverse exist. So let's get into that. Then open parentheses A comma B close parentheses open parentheses A to the negative 1 inverse of A, say comma B, the inverse of B close parentheses is equal to open parentheses A close circle A the inverse of A comma B open circle the inverse of B close parentheses is equal to open parentheses 1 comma 1. That's what we wanted. That's exactly what we've got. So let's go to the other side of things, right? So open parentheses A inverse of A comma inverse of B close parentheses open parentheses A comma B close parentheses is equal to so yeah, you just look at that directly. So A inverse of, open parentheses inverse of A close circle A comma inverse of B open circle B close parentheses, and that is equal to 1, open parentheses 1 comma 1 close parentheses. So yeah, we have, so open parentheses A, the inverse of A comma B the inverse of B. So open parentheses inverse of A comma inverse of B, it's not a 2, that's supposed to be a 1, is a two-sided inverse of open parentheses A comma B close parentheses. So we've went through, we have that, therefore, we can say therefore A cross B satisfies closure, associativity has identity, open parentheses 1 comma 1 close parentheses, and every element has an inverse. Hence, A cross B is a group under component-wise multiplication, as is required. So that, finish off this exercise and move on to the next one, which is 29. Oh boy, okay. check the camera real quick. Camera's good. Right, so this one's this one echoes what we've looked at before. It's a bit interesting now. So we looked at 28. Who's at the inverse of that? Right, so 29. So exercise 29, it asks us to, it says prove that A cross B is, it's not just a group, it's an abelian group if, it's an abelian group if and only if both A and B are abelian. So what's the intuitive sort of groundwork that we can have with this? Well, the product law on A cross B is component-wise as it was earlier, right? So open parentheses A sub 1 comma B sub 1 close parentheses open parentheses A sub 2 comma B sub 2 is equal to open parentheses A sub 1 close circle A sub 2 comma B sub 1 open circle B sub 2 close circle. So open parentheses A sub 1 comma B sub 1 close parentheses commuting with open parentheses A sub 2 comma B sub 2 is exactly the pair of statements A sub 1 close circle A sub 2, which is equal to A sub 2 A sub 2 close circle A sub 1 in A, and B sub 1 open circle B sub 2 is equal to B sub 2 open circle B sub 1 in B. So we want to prove both directions. That's the intuition there. So let's I'm gonna check this, and then I'm gonna get back to looking at that more rigorously. Because it's an if and only if, right? So this would be if A cross B is abelian, then A and B are abelian. So assume, right? So we want to show it's already an abelian group. It's already a group. It's already, we already have it. It's important, right? So I mean that's implied, but A cross B is abelian, then A and B are abelian. So how do we usually prove this, right? How do we usually prove this in a case which doesn't involve scary amount of parentheses and commas? Well, we'd say, okay, if you can swap places with them, right? If they're commutative, then there you go. So you put up an arbitrary example of that. Well, you put up not just an example of that, but it's like the arbitrary case for this, right? And then you'd say, okay, because of the fact that that holds, we can say that this is abelian. So let's go ahead and do that just now. So assume open parentheses a sub 1 comma b sub 1 close parentheses open parentheses a sub 2 comma b sub 2 close parentheses. Assume, well, that this is equal to open parentheses a sub 2 comma b sub 2 close parentheses open parentheses a sub 1 comma b sub 1 for all a sub I within A and B sub I within B, because it's arbitrary. Well, then what can we say about this? Well, then open parentheses a sub 1 close circle a sub 2 comma b sub 1 open circle b sub 2 and close parentheses, that's equal to open parentheses a sub 2 a sub 2 close circle a sub 1 comma b sub 2 open circle b sub 1. Now the equality of ordered pairs which is what we're working with here, right? So the equality of ordered pairs forces equality in each component. What do I mean by that? Well, do we actually have enough room for that? Let's see. Yeah, there is enough room. It's just going to be a bit of a squeeze, so I'll have to erase this. But equality of ordered pairs forces equality in each component. So what can we say about our situation as it exists right now? Well, a sub 1 close circle a sub 2, well, that's equal to a sub 2 close circle a sub 1, and b sub 1 open circle b sub 2 is equal to b sub 2 open circle b sub 1. So we have our commutativity there, and this isn't just for these two instances. This was an arbitrary case because, well, I mean, we could say, right, I suppose. Well, actually, could we actually say that? Let's think about that. No, we can't. No, wait. Could we actually say that? I think so. All choices. Those are abelian. No, because we're saying, I mean, in a way that's already arbitrary enough, right? So, because we're saying any two, and the only reason, this is just for indexing, so I think that should hold. Correct me if I'm wrong. That should hold. This is for all choices. All choices of a sub I and b sub I. Right, so equality of ordered pairs forces equality in each component in this case. So yeah, we can say that that's the case. And because of that, well, we have our commutative operation shown right there with each of the elements. And so we could say, therefore, A and B are abelian. Abelian. Okay. So now let's go the other way. So we want to say if A and B are abelian, then A cross B is abelian. So let's assume, the same approach as earlier, just a bit different, because we're swapping this. Assume A sub 1 close circle A sub 2 is equal to A sub 2 close circle A sub 1 in A. And B sub 1 open circle B sub 2 is equal to B sub 2 open circle B sub 1 in B for all elements. Then for any open parentheses A sub 1 comma B sub 1 close parentheses comma open parentheses A sub 2 comma B sub 2 close parentheses within A cross B, well, then for any such ordered pairs within A cross B, we have that open parentheses A sub 1 comma B sub 1 close parentheses open parentheses A sub 2 comma B sub 2 close parentheses is equal to open parentheses A sub 1 close circle A sub 2 comma B sub 1 open circle B sub 2 close parentheses, which is equal to open parentheses A sub 2 close circle A sub 1 comma B sub 2 open circle B sub 1. Right, so, and this would be equal to open parentheses A sub 2 comma B sub 2 close parentheses open parentheses A sub 1 comma B sub 1 close parentheses. So we showed it directly. So because of that, A cross B is abelian. Hence, A cross B is abelian if and only if A and B are abelian. So that's exercise 29 out of the way. Let's go on to exercise 30. It's an exercise. All right. So for exercise 30, we have prove that the elements open parentheses A comma 1 close parentheses and open parentheses 1 comma B of A cross B commute and deduce that the order of open parentheses parentheses a comma b is the least common multiple of the order of a and the order of b. That's interesting. Okay. So in the direct product, everything is component-wise. So open parentheses a comma 1 close parentheses x only on the a coordinate, and open parentheses 1 comma b close parentheses only on the coordinate. Hence they commute. Power is also split. So open parentheses a comma b close parentheses to the n is equal to open parentheses a to the power n comma b to the power n close parentheses. Therefore, the smallest n, which terminates both coordinates, is exactly the least common multiple of the order of a and the order of b. So let's get to showing that a bit more rigorously with a proof. So, right, so, well, work in A cross B with the component-wise law open parentheses A sub 1 comma B sub 1 sub 1, there we go, close parentheses, open parentheses A sub 2 comma B sub 2, close parentheses is equal to open parentheses A sub 1 A sub 2 comma B sub 1 B sub 2, close parentheses. So first off, we want to look at the case of whether or not open parentheses A sub 1 comma, open parentheses A comma 1 close parentheses and open parentheses 1 comma B commute. So I guess I could just say the ordered pair 1 comma, but that's actually harder for me to say. So oh well. Open parentheses A comma 1 close parentheses and open parentheses 1 comma B commute. So let's compute both products. Let's see whether or not that's the case. Open parentheses A comma 1 close parentheses open parentheses 1 comma B. Well, that's just equal to open parentheses A close circle 1 comma 1 close circle B, which is equal to open parentheses A comma B close parentheses. Now let's look the other way, just to say open parentheses 1 comma B close parentheses open parentheses A comma 1 close parentheses is equal to open parentheses 1 close circle A comma B close circle 1 close parentheses, which is equal to open parentheses A comma B close parentheses. So yeah, so they do actually commute. These things are equal. Doesn't matter which way you change them. So yes. We already have this stated up here, so I'll just put a check mark. let's go on to the next part, which is to, this is actually 3 parts. This is actually 3 parts long. Yeah, because we got to prove those elements commute and deduce that order is the least common multiple. Well, actually, I don't know. Let's see. Well, we'll need to go on to a second part in order to prove the last part, so let's go ahead and go on with that. Right, so power split. We said that in the intuition, but let's see if we can look at that more rigorously. Well, what do we want? We want open parentheses a comma b, close parentheses to the n. We want that to be equal to open parentheses a to the n comma b to the n close parentheses. That's what we want. When do we want it now? But we can't have it now. We have to prove it. So, and we want this for all n within the positive integers, right? So how would we go about doing that? Well, with any sort of thing involving these exponents, like we mentioned earlier, we're going to have to use an inductive argument. So let's have, well, induction on n. For n is equal to 1, it is immediate, because that's equal. So if, I mean, that can be our base case, right? So now onto the inductive step, right? So if open parentheses a comma b close parentheses to the power k is equal to open parentheses a to the k comma b to the k close parentheses, then well, open parentheses a, well, this is our inductive step, right? This is our inductive step. This is our inductive hypothesis is what I'm trying to say. This section, this if, right? So let's assume that holds. Well, if we assume that holds, then we can say a comma b, I mean open parentheses a comma b to the k plus 1 is equal to open parentheses a comma b close parentheses to the k close parentheses a comma b, I mean open parentheses a comma b close parentheses, and that is in fact equal to open parentheses a to the k comma b to the k close parentheses open parentheses a to, I mean a comma b close parentheses, which is equal to open parentheses a to the k plus 1 comma b to the k plus 1 close parentheses. So so the formula holds for all n greater than or equal to 1, right? So come on. That looks like a 1 enough, right? So I mean, it's missing a little. See, you do this a while enough and you start to get lazy, and then the 1s start to look like 2s, and that's when everything's get really annoying. But I mean, for now, I mean, anyway, the inductive step holds, so this entire thing holds. So the power splitting thing, we have that. We have that the power splitting thing works, that's logically consistent, that's proved. Now we can finish this off at step 3 to really deduce the order of open parentheses a comma b close parentheses. Let's do that. Gotta make So right, so part 3 of this proof, deduce the order of open parentheses A, comma, B, close parentheses. Now, right, so if it has a prove that the elements so can we say, can we assume the order of A and the order of B are finite, less than infinity? I mean, if it's infinite, then it doesn't really matter. Though, I don't know. I'll have to look further into that because let's see. But if it's infinite, then prove that the elements A cross B commute and deduce that the order of AB is A comma B is the least common multiple of order A and order B. So we'll see about that. For now, let's just assume the order of A and the order of B are, make note of that, just in case. So does that even, I mean, but we're using, it's saying that these things commute, prove that the elements commute, show that it commuted. To say these things. Okay, I'll look at that more in depth, but for now, let's just assume that the order of A and the order of B, that those are less than infinity. Let's assume that these are finite, and let's set L equal to the LCM of the order of A and the order of B. Well, what do we wind up with then? The open parentheses A comma B, close parentheses to the power of L is equal to, we use that power splitting thing that we had earlier. So open parentheses A to the power to the L comma B to the power of L, close parentheses is equal to open parentheses 1 comma 1 close parentheses. And this is, since in order for any of this to work, it has to be it has to be finite, right? So that's something I wish the wording, unless if the wording is different in the book and I didn't transcribe it correctly from there into my notes, but I feel like there's got to be a way, though, that you could explain that this has to be finite. Anyway, is equal to open parentheses 1 comma 1 close parentheses. Since the order of A divides L by definition, and the order of B divides L by definition of order of the element, so therefore, the order of open parentheses A comma B close parentheses is actually less than L. Ooh. Less than or equal to L. And conversely, let me get this thing out of the way. Conversely, if open parentheses A comma B to the L is equal to open parentheses 1 comma 1 close parentheses, then, well, then by our power splitting argument, what we have is that open parentheses A to the K comma B to the K close parentheses is equal to open parentheses 1 comma comma 1 close parentheses, which implies that A to the K is equal to 1 and B to the K is equal to 1. So we've shown that, like, well, look, we follow along this argument where we take L equal to the LCM of the order in A and B, and look where it gets us. It gets us exactly right back to the definition of what exactly the order of an element actually is. So for an element to have an order in finite, in the finite case. So the order of A divides K, right? And the order of B divides K. Therefore, K is a common multiple of the order of A and the order of B. So what does this mean more to the point? Well, so that's important, but so L is less than or equal to K. Therefore, the order of open parentheses A comma B is equal to L, which is equal to the LCM of the order of A, the order of B. Let's see if this makes sense, right? So yeah, because we looked at each case, we looked at both the so we showed that must be less than or equal to L, and then we swapped them, and then we said, okay, if we do it that way around, without having to define it directly, would this sort of structure emerge? Does emerge. So these things are actually equal. So the order of open parentheses A comma B close parentheses is equal to L, which is equal to K, which is equal to the LCM of the order of A and B. Correct me if I'm wrong, but I think that's it, because Well, we have that open parentheses a comma 1 close parentheses and open parentheses 1 comma b close parentheses commute, and the order of the ordered pair of a and b is equal to the LCM of the order of a and the order of b for finite, which we weren't explicitly told it was finite, so at least from my notes, from what I've transcribed, so that's something that could be an issue. So far, I think that holds. Alright, gotta get up. Oh no. So let's go on to exercise 31. So exercise 31 asks us to, well, prove that any finite group G of even order contains an element of order 2. Prove that any finite group G of even order contains an element of 2. So, you know, the fact that you have order 2 being mentioned here, something you're trying to, well, something that's even order is like, well, even 2, right? That thing sticks up like a sore thumb. Well, intuitively speaking, pair every element G that is not its own inverse with the inverse of G. These come in disjoint 2-element packets. Since the order of G is even, what remains after removing all such packets still has even size and contains the identity element. Hence, there is some non-identity A, with which A is equal to its inverse. So, like, for example, A squared is equal to the identity in involution, in a way. But it's more abstract than that, because an involute is like, you know, x squared is equal to 1, but in this case we're looking at like a squared is equal to the identity. So, so let's look at how we would solve this, well, prove this more rigorously from that intuition. So let's let G be finite. We are explicitly told that it is, with the order of G being even. Let's define some function t of G equal to the set containing G within the group G, such that G is not equal to its own inverse. Right, so think about this. does that work? Define T of G to be equal to this set of things. Why would we do that? We want to look at a mapping, right? So let's look more closely at this. T of G has even cardinality. That's what we want to look at, pairing by inverses. That's what we want to look at. We want to be able to pair every element G that is not its own inverse with every element G that is not its own inverse with the inverse of G. So that's explicitly what this function is for, right? So, and we want to find that special case. So T of G has even cardinality, pairing by inverses. So let's consider the map L, which maps T of G to T of G given by L of G is equal to the inverse of G. If, what we say here, if G is an element of this T of G, well, then quite naturally, right, G cannot equal its inverse. It's defining character. No, it's characteristic. I don't want to say characteristic because that's like an actual thing. So that's true. So what? So the inverse of G, that can't be equal to, open parentheses, inverse of G, close parentheses, to the power of -1. It can't equal the inversion of itself, which is equal to G. So G, the inverse of G, is also contained within T of G. Now, but if we take the function L of G, well, then we'll get that that's equal to G, open parentheses, the inverse of G to the -1 which is equal to G. Which is a problem because I need to put... No, we made it a map to itself. We made it a map. We made it a map to itself. How does that work? So given by it's equal to its inverse. Okay, okay. We inverted. What is it? Like yeah. So let's take a look at this let's continue along this path. Take a look at it from more expanded angle. Yeah, you can see it inverts the mapping. Inverts the mapping? It's a more precise way of saying that, but it's an inversion of what that's supposed to be, the function t is supposed to be. So it's like, well, we can say that that is the case there. We can say that this is the case here, under this function. Under this function, we can say that this is the case, but we couldn't say it's the case within t because that's like, it goes against the definition of what t is. So, so L is an involution with no, I mean, yeah, okay, with no fixed points. On T of G. Yeah. That makes sense, right? Let's see about that. So we have that L of G is equal to, open parentheses, G inverse, the inverse of G, close parentheses, that inverted, which is equal to G. So L is an involution with no fixed points on, on T of G. So you'd ask, like, okay, well, what's the big idea there? Well, because of that, T of G is a disjoint union. It's a disjoint union of two elements sets containing G and inverse of G. So the order of T of G, these things are distinct. These things are what is in T of G. And so the order of T of G is even. Find a case such that it does map back to it, but these things are still not equal. Ergo, yeah. Okay, so, but we still have a lot of work to do on this one because, let me check the, yeah, it's still working on. So, we managed to find that the order of T of G is even, but what about G as a whole, right? We still haven't gotten to that, so. Oh, well, prove that any finite group G of even order contains an element of order 2. We haven't proved that there exists an element of order 2. All we've proven is that this function on G, this function of G, the group G, has that order. But, let's continue. So we want to say that there exists a non-identity element equal to its own inverse. And why do we want to say that? Well, if you remember from the intuition, you know, we want to be able to say that a squared is equal to e. We want to be able to say that there exists an element of order 2. So, since the order of g is even, and the order of t of g is even, their difference, this is a bit of a, this covers some stuff that we haven't covered in the book, but I think there's, intuitively speaking, like their difference, right? So it's like the order of g with the exclusion of that set, right? That set that's defined by this function is equal to the order of g minus the order of t of g. That should be even. So it's like, well, you know, you can think about this intuitively. It's like, what's, you take away 2 from 4, what's that? That's 2. You take away 6 from, you take away 4 from 6. It's like, well, that's 2. And then, you know, you subtract an even from an even. Their difference is even. Now it's important to note, I'll get into this in just a moment, note that the identity element itself does not exist within t of g, and this is because e is its own inverse, right? So the identity is its own inverse. Hence, e is contained within g cross t of g, and g cross, g, well, e is contained within g excluding t of g, and g excluding t of g is a non-empty set. So, because the order of g excluding t of g is even and already contains e, there exists a within g exclusion g excluding t of g with a not equal to the identity. There must be something out there that is distinct from this thing. So it's like, well, of course, because if it was the case, if this was the case, then you couldn't say that this thing is even, right? So then because there would only be one thing, there could only be one thing. So by definition, of g with the exclusion of t of g, we have a is equal to its inverse. So a squared is equal to a dot a, which is equal to the identity element, and this is without a this is with A not being equal to the identity. Ergo, A has order 2. And there it is. This proves that every finite group of even order contains an element of order 2. How much time do we have left? Not much, if at all. And 32 is rather long. So, I mean, 32 is not long, it's just, well, we're meeting our time quota for now, so let's leave it at that. And we will pick up with exercise 32 in the next portion. Well, 32. We just finished 31, so yes, 32. Yeah. Alrighty then.